morning, students. Today's class we are going to learn what is a full wave rectifier. In the last video, you might have learned what is a half wave rectifier, how it is employed with the help of a single PN junction diode, and what are the advantages and disadvantages of a half wave rectifier. So in the half wave rectifier, you might have seen the ripple factor is more and the efficiency is only 40.6 percentage, which is very less. So in order to overcome all those disadvantages, we are going with a full wave rectifier. A full wave rectifier conducts during both positive and negative off cycle of the input AC supply. In order to rectify both the off cycles of the AC input, two diodes are used here. So the diode feeds a common load RL with the help of a center tap transformer. And the AC voltage is applied to a suitable power transformer with proper turn ratio. So the full wave rectifier circuit is shown here. So as we have discussed in the last class, there are two types of full wave rectifier. One is the center tap full wave rectifier and the other one is a bridge rectifier. So let us learn what is a center tap full wave rectifier. So in the center tap full wave rectifier, we have employed two diodes and it is named as D1 and D2, and the input AC voltage is applied across a center tap transformer and a common load is fed across the diodes and it is represented as RL, and the output voltage is taken across the load resistor RL. So what is the use of making use of this center tap transformer is, it will be having 3 points where it is named as A, B, and there is a center point named as center tap, which is shown in the circuit. So let us know how it works. During the positive off cycle of the input AC voltage, the diode D1 will be under forward bias. Why? Because during the positive off cycle, the point A will be at positive and point B will be at negative. So when a positive potential is connected to the P-type of the PN junction diode D1, the D1 will be under forward biased, whereas the point B is negative and it is connected to the P-type of the diode D2, which becomes reverse bias. So during the positive off cycle, only one of the diode will be conducting, that is the diode D1, and you can expect the output across the RL, which is the output due to the conduction of D1. So this can be observed in the waveform given here. So the first one represents the input AC sinusoidal signal, and during the positive off cycle, that is from 0 to pi, you can observe there is a output voltage and output current across the load resistor, and it is represented as D1 on. And during the negative off cycle, the point A will be negative and point B will be positive. When the point B is positive, D2 conducts and D1 does not conduct, and it will be under reverse bias. So during the negative off cycle, you can observe we'll be getting an output DC voltage across the load resistance RL, and it is due to the conduction of diode D2. Hence it is represented as D2 on in the output current and output voltage. The same phenomena repeats for the other cycles of the input AC voltage. So let us learn what is the efficiency of employing this two diodes using a full wave rectifier. As you have seen, what is the efficiency parameter, which is defined as ratio of DC power delivered to the load to the AC input power from the transformer efficiency, which is nothing but PDC divided by PAC. And PDC, the power can be represented as I square R, and hence PDC is equal to IDC square into RL, and PAC is nothing but the power input power from the secondary of the transformer, which can be written as I RMS square of RF plus RS plus RL. What is RF is the forward resistance of the diode during forward bias, and RS is the resistance of the secondary windings of the transformer, and RL is the resistance of the load connected. And since it is the AC voltage, the current will be represented as IRMS. So let us divide PDC divided by PAC to get the efficiency. So we have written eta is equal to IDC square RL divided by IRMS square into RF plus RS plus RL. And if the load resistance is considered as much greater than sum of RS plus RF, you can neglect the parameter, and finally you will be getting as eta is equal to IDC square divided by IRMS square. And for the full wave rectifier, since we are getting the output twice that of the off wave rectifier, IDC can be written as 2Im by pi. Whereas for the off wave, we had IDC is equal to Im by pi and IRMS is equal to Im by root 2. By substituting these parameters IDC and IRMS for eta, we will be getting finally a value as 0.812. In terms of percentage, it is 81.2 percentage. That is, we are getting a maximum efficiency of 81.2 percentage, which is more than that of a rectifier. And remember, for the off-wave rectifier, we have 40.6 efficiency, whereas for the full wave rectifier, we are getting 81.2 percentage. Let us learn the ripple factor also for the off-wave rectifier. As already we have seen, what is the definition of a ripple factor? It is nothing but ratio of IAC by IDC. By substituting the parameter for IAC and IDC, we are getting eta as after substituting different parameters of IRMS and IDC for the full wave rectifier, we are getting the ripple factor eta is equal to ripple factor is equal to 0.482. In terms of percentage, it is 48.2 percentage. As I told you in the last video that the ripple factor has to be less, then only we can expect the output without any ripples. That is, you will be getting a pure DC voltage without any ripples. So let us see what are the advantages and disadvantages of the full wave rectifier. As just we have derived, the ripple factor is ripple factor is 0.48, and the efficiency is also very high, which is 81.2 percentage. And since we are making use of a center trap transformer, will not get any DC saturation because of the secondary winding employed there. And DC output voltage and DC current are also twice as compared to the off-wave rectifier. And disadvantages, if you see, it is expensive because of use of the center tap transformer, and it is difficult to locate the center tap of the secondary winding of the transformer employed here, and the output voltage is off of the secondary voltage, and diodes have a high peak inverse voltage and which is larger in size, and it is costlier. And the peak inverse voltage of the diode, if you see, it is 2 times that of the off-wave rectifier.